Let's continue on with our discussion of autocorrelation by talking about the Durbin-Watson test. So we're sort of bringing together all the knowledge that we've gathered about the two different types of autocorrelation: negative autocorrelation, positive autocorrelation. Negative autocorrelation meaning that if you have a negative error, it's followed typically by a positive error, then followed by a negative error, and then followed by a positive error. Now, it's not always that clear cut, but that's the theme or the predominance of the relationship. Whereas positive autocorrelation is kind of like little smile kind of thing, very devious little smile. A positive error is followed by another positive error. A negative error is followed by another negative error. Now, the Durbin-Watson test statistic measures what we call first-order autocorrelation. That's just a really fancy way of saying what we're concerned about is the error in the one immediate preceding time period. Okay, so like a simple linear regression, for instance, where we're trying to predict error in the current time period based on error in the most recent time period. There are things kind of second-order autocorrelation. It's a thing that does exist, and then you're looking at epsilon t minus 2 and so on, and it can get really complicated. First-order autocorrelation captures autocorrelation most of the time, and if autocorrelation exists, it's mostly first-order autocorrelation. So this Durbin-Watson statistic and test is very helpful in helping us diagnose autocorrelation most of the time. But there are other types of autocorrelation that do exist, and it doesn't hurt to be aware of that. So when we look at this equation, we see as a coefficient in front of epsilon t minus 1, not a p, but rather the Greek letter rho, R-H-O, if you're trying to type it out. So it's the Greek letter rho there. And that's the coefficient in front of epsilon t minus 1. If that we want that coefficient to be equal to 0, because if that coefficient is equal to 0, that means there's no relationship between epsilon t and epsilon t minus 1, which is great, right? We don't like relationships between our errors, because if there's a relationship between the errors, it means our model's missing something. So we want that Greek letter to be 0. And we can conduct a test and see, hey, is it significantly different than 0? And if it is, we got a problem. And if it's not, we're reasonably happy. Okay. So you can kind of imagine that if that Greek letter rho is positive, guess what? A type of autocorrelation you might have. Positive autocorrelation, right? If it's negative, then what kind of correlation would you have? Negative autocorrelation, right? And we saw this relationship when we did the scatter plots of ET versus ET minus 1. And notice I used the letter E. That means because those were actual results that we had from our regression. Okay. So, and we saw that when we had sort of a negative relationship between the two. We looked at the diagram and we said, hey, that's negative autocorrelation. And in the situation where we had a positive relationship between ET and ET minus 1, we said, hey, that looks like we looked at the time sequence plot, and hey, that looked like the little smile, and hey, we have positive autocorrelation in that particular case. Don't worry about the mu t. I know, I get it. 24 letters in the Greek alphabet. We use mu so many times for so many different things, and spoiler alert, we'll use it again in ANOVA. But it just means the error of the errors. I know, sounds a little bit mucky. Sounds a little confusing. Luckily, we're not going to interact with it too much. It's there for just to set out the theoretical underpinnings or the conceptual underpinnings that's going on here as to what this Durbin-Watson statistic is looking for. Okay. So we don't have to worry about it too much. We do hope that rho is equal to 0, and we are concerned if it's not. So the Durbin-Watson test statistic, it typically will use technology or a computer program to measure. It's a little bit messy. You can kind of see, lots of calculations, both in the numerator and in the denominator, and they all find in errors, and we're summing stuff up, and it is a little bit mucky. Okay. Luckily, we can get a statistical package to do the calculation for us, and it does all that grunt labor instead of us doing the grunt labor. We'll be thinking about the interpretations, the implications, possible solutions. That's the big brain stuff, and that's what we'll focus in on. We'll let the computer packages do the mindless, knuckle-dragging grunt calculations. Now, the Durbin-Watson test statistic is a little bit set out differently than what we've become accustomed. Okay, so it's a little bit different style of representation. It doesn't follow the nice little parametric distributions that we've come to know and love, like the F distribution, the chi-square distribution, the T distribution, and so on. Okay? So we have a little bit different setup. HO is we do make the assumption, as one of our 4 assumptions, that the errors are not related to each other or not autocorrelated. And so that's our assumption, which means that flows nicely into what we would expect HO to be. We assume that the errors are not correlated unless we establish otherwise. And HA is where we establish the otherwise. Now, a couple of observations here. We have a zone, so we will look up in tables. Now, there's no way getting around the tables. There's no nice little Excel functionality for the Durbin-Watson test statistic. The table is really easy to use, so it's not complicated in that sense, but it is a little bit of different than our other distributions that we've used so far. So we see we have a zone or an area of positive autocorrelation, and we have a zone of negative autocorrelation. And ironically, the positive autocorrelation is on the left, negative autocorrelation on the right. Okay? Now we have what's called a DL and a DU, and that's a Durbin-Watson lower, Durbin-Watson upper. So DL and DU. And those are the 2 values we look up in the tables. And then, so we have a zone, and if you're below the Durbin-Watson lower, right, so if you have a Durbin-Watson test statistics that's lower than this particular value, that indicates that you have positive autocorrelation. Okay? If you have a value higher than the Durbin-Watson upper, then it indicates, first of all, no positive autocorrelation. And if it's between the Durbin-Watson upper statistic and 4 minus the Durbin-Watson upper statistic, if it's in that range, that indicates no autocorrelation of any type. Why 4, you might ask? 4 is the biggest number for a Durbin-Watson test statistic. So 0 is the smallest number, 4 would be the biggest number. Now you'll notice, and then same kind of symmetry for negative autocorrelation. If you go 4 minus the DL and you get a Durbin-Watson test statistic bigger than that, that indicates negative autocorrelation. Now, something unique with the Durbin-Watson distribution, if you will, for lack of a better term, is you got this question mark stuff. Like, question mark? What do you mean question mark? And before, yeah, there is or what isn't. Significant or not significant? What's this question mark stuff? Well, because of the limitations of the distribution, there are certain zones where we're unsure. So where you see a question mark close to the positive autocorrelation, that's where it's probably positive autocorrelation, but we're not sure. Same thing with the little question mark close to the negative autocorrelation. It's probably kind of negative autocorrelation, but we're not sure. And this typically becomes an issue in cases where we have small sample sizes. Okay, so that the range between, let's say, the DL and the DU is wider for small sample sizes than it is for big sample sizes. And as the sample sizes get really, really big, that little question mark or uncertain zone gets smaller and smaller and smaller. Okay, so it's just the limitations of the Durbin-Watson test with small samples. Okay, and that limitation is such that when we look at the tables, for instance, we see that N, the sample size, starts at 15. Okay, so we typically would not use the Durbin-Watson test for samples under 15. Now you can look at the ranges between the DL and the DU, and you can kind of see it. N is equal to 15. It's between 1.08 and 1.36. And as we scroll down to 37, for instance, and our tables go up to 100, it goes down to 1.42 to 1.53. So it's getting smaller again, and that's what we would expect. Also on this table, you see a k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5. That is, the k represents the number of independent variables. number of slopes. Now, I get it, K, it only goes up to 5. It works for 5 and higher than 5 as well. It's just that we've got a little bit of limitations in our tables. Okay, the next thing is we have a separate table for each alpha. That's somewhat unique. So there'll be a table for alphas 0.05, there'll be another table alphas 0.025, and a table for alphas 0.01. Okay, so that's also something to keep in mind. There's also a little trick with the Durbin-Watson test statistic that you'll hear me mention this again, is when Durbin and Watson first came up with the Durbin-Watson test statistic, they only cared about positive autocorrelation. That was the one that they thought was most egregious, the most problematic one. Negative autocorrelation, not really a big deal to them. And positive autocorrelation is a really big problem. So everything is sort of set up to diagnose positive autocorrelation. That's why the DL and the DU are on the positive side of the autocorrelation number line, if you will. Okay. So it's set up there, and then later on, you know, they've sort of adapted this structure to deal with diagnosing negative autocorrelation. So negative autocorrelation is kind of like an add-on. It's like a glue-on, right? We went looking for positive auto, and then, okay, we got it. We got a test that somewhat, you know, finds it, helps us diagnose it. It's better when sample sizes are big than when sample sizes are small. And then people started thinking, well, what about negative autocorrelation? That could be problematic too. I mean, that's related errors as well. And so they've sort of adapted it to look for that as in addition. Okay. So we've got those two things flown around, and we kind of see table. We just sort of match it up, right? We get a certain sample size, match it up with how many independent variables are. We get a DL, we get a DU, we start plugging it into the number line. Right? So step 4 is essentially plugging stuff into this number line. So kind of easy peasy, right? Looking up two values in a table, writing them down in the number line, going 4 minus those two little numbers to get some ranges for the negative side of the autocorrelation number line, if necessary, and off we go. Okay, so in theory, if you were to do this on Excel, and if you really wanted to do it on Excel, you'd run the regression, you'd find the residuals, you plug them into that Durbin-Watson formula. So with Excel, it's not so bad because you can set it up to do those calculations and do that grunt calculation for us. Additionally, you could use another statistics program such as SPSS or PSPP, which is an open source version of SPSS. The GNU has a version of a stats program that looks a lot like SPSS as well, or PSPP, the new GNU version. Those are all open source, so they're free. There's programs like Stata and so on. And then they'll find the Durbin-Watson test statistic. You just have to, you run your diagnostics, you click a box, you pick Durbin-Watson, easy peasy, out comes the number, and it's quick and set up. So to recap just a little tiny bit, and then start to work on an example. So when we start to formulate our HOs and our HAs, we see questions. So for instance, does the error show first order calculation? Now notice we're just asking about, essentially, does autocorrelation exist? Yes or no? And we don't care if it's positive auto, we don't care if it's negative auto. Right? We don't care if rho is a positive slope or if rho is a negative number. We don't care, right? Either way, find me something. And in that case, HO is that we assume, again, no auto, and rho is equal to 0 versus rho is just not equal to 0. And then we can also be asked the question, does the error show first order positive autocorrelation? Okay, is there evidence of positive auto? Well, in that case, we're looking to see our HOs that we're testing whether the Greek letter rho is greater than 0. Is it a positive number? Right? And then HO is always the opposite of HA, so is it less than or equal to 0? Negative autocorrelation, does the error show first order negative auto? Well, then HA would be that rho is a negative number. Okay, so rho less than 0 versus HO being the opposite, rho is greater than or equal to 0. And so we have all three versions of this test. And those are basically the three types of questions that you'd see. Does the error show first order autocorrelation? That's where we don't care. Is rho just not equal to 0? I don't care if it's positive or negative. Any auto. We have, does the error show first order positive autocorrelation? Then we're looking for that rho being a positive number. Or does the error show first order negative autocorrelation? And we're looking for rho is at a negative number. Okay. So those are our three flavors of autocorrelation. So let's look. We get our output, and even though for our purposes Excel does not generate a Durbin-Watson test statistic, I will put it in the middle area there, just above the coefficients, just below the little ANOVA part of the regression. Okay, just so that it's in a place that you can find it. If that doesn't work, or for whatever reason, I might just give you the Durbin-Watson statistic itself, and that'll have been derived. For me, it would have been derived from R. I find that's the quickest and easiest, cheap statistical program for me to use. Okay, so we're asking ourselves the question, does the Durbin-Watson test indicate first order autocorrelation in the error term? So when we think of our step 1, we think of HO, we think of HA, and it just says, does it indicate first order auto? So it doesn't say a particular flavor of autocorrelation, just any autocorrelation. So we go Greek, that Greek letter rho not being equal to 0 versus the Greek letter rho equal to 0. Step 2, we assume an alpha is equal to 0.103. I'm sorry. Step 2, alpha equals to 0.10. I have no idea what happened there. Step 3 is we just report the Durbin-Watson test statistic, which is 1.867878. Step 4 is where we draw out that little number line. Okay, so it's asking for any auto. So we kind of look at our number line, and we'll have some components to that number line. So we'll have a zone where there's positive auto. We'll have our little question mark zone. We'll have our no auto zone. Right? Not to scale, by the way. We'll have our question mark zone, and then we'll have our negative auto area. Right? So we're going to look up in the tables the Durbin-Watson lower and the Durbin-Watson upper in this case. Okay. Now, when I said, you look at it and said, hey, Alan, hey, look back here. Psst, buddy. We only have tables for alpha is equal to 0.05 and alpha is equal to 0.025 and alpha is equal to 0.01. Like, gee, this is awkward, but where's the table for 0.10? Hey, guy. Hey, buddy, what happened there? Well, the thing is, remember that I was telling Durbin-Watson really only concerned about positive auto? So this is all zero. These critical values are all zeroed in for positive auto and positive auto only, which means when we start to look up those Durbin-Watson values, the DL and the DU, we take that alpha, we divide it by 2, okay, so that we can look in just the one side, and then we'll do the 4 minus to get the other side. So we really stuck taking an alpha over 2. So alpha over 2 becomes the important value that we start looking for. And alpha over 2 is 0.05. Okay? So let's pull in the table here. I'll just pull in the table. We'll have a table of fun. Okay, so here we have a Durbin-Watson table. Now, if we look back at the output, we would see that in this case, we had n of 16. So we had a sample size of 16. And in those particular results, we only had one independent variable. And you could go look at the output and verify that. Okay. So now we look at n is equal to 16 and k is equal to 1. And we see that we're in alpha of 0.05 because remember we divided by 2 because the tables are set up for looking only for positive auto. So now we're looking on both ends negative auto and positive auto. So we're taking a one-tailed table, transforming it into a two-tabled case. We've done the reverse a little bit. We talked about that way back when we were talking about Z tables and so on. Now we just kind of looking at it the other way. So we get our numbers and we see that the K is lower is 1.10. So I go 1.10, and I'm sorry, a little bit squishy there. Okay, and my upper is 1.37. So upper 1.37. Okay, and now I set up my 4 minuses. So 4 minus 1.1. And so that just tells us that that's a 2.90 up there. And 4 minus, oops, sorry, I got that mixed up. 4 minus 2.1, that's this one right here. Sorry, kind of messy here. 2.09. And then 4 minus 1.37. And in that case, we get 2.63. Okay, so we follow, if you get all confused like me, we just follow the number line, smaller numbers to bigger numbers, okay? So that's our step 4. Step 5 is now we look inside. We actually look in the line. Where did our 1.86 fall? Well, it fell between 1.37 and 2.63, okay? So the dW is equal to 1.867878. Falls between 1.37 and 2.63. So we do not reject HO in that case, right? Because that indicates no auto. Not reject HO, right? Again, no auto. That's this one right up there. And so in step 6, say no evidence of autocorrelation. If you want to get really technical, and I probably should, no evidence of first order autocorrelation. But our theme so far in this course is we're trying to minimize a little bit of the stat speak in that step 6. Hard to do when you use the word autocorrelation. You could say no evidence of that the errors are related to each other. If you prefer to kind of, simplify it a little bit further and take maybe a step down from the stat speak. But so our theme has been to try to minimize stat speak in step 6. So I've sort of avoided the first order autocorrelation because that just gives everybody a headache, right? Okay. And so there's our 6 steps. And let me pull the table away again. And we can go through, and then here's some wordy explanation of where the numbers came from, in case you forget, and so on. And, what's in the interval, blah, 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 conclusion. And again, technically, when I put it on the slides, I included the word first order autocorrelation. Sometimes I'm prone to being too statsy myself. So first order, not really critical issue, but just, we say that there's no autocorrelation here. Okay. So we'll do this example in a moment. I just want to jump ahead and say, here's our 6 steps, right? And this is what we've followed so far. We've stated the hypothesis. Right? We've stated the alpha, like we always do. The Durbin-Watson test statistic is given to us. Helpful to also note that what the n is and what the k is, because it'll be useful when we get into step 4 and we start drawing out the line. Step 5, we make the decision using that line, looking to see where our Durbin-Watson statistic falls in that line. Right? And are we rejecting H naught or not rejecting H naught? And then step 6 is we just state our conclusion. Do we have evidence of autocorrelation if that was what the question was? Do we have evidence of positive auto if that was what the question was? Negative auto if that was what the question was? Okay. So we have that. So let's jump back into the slide a little bit. Okay, and let's ask ourselves the question with this particular slide 38. Is there evidence of positive autocorrelation? Okay, here's our question, and let's assume alpha is equal to 0.01. Just so we're using a different table, just for a little bit of fun and variety, right? We like fun and variety. Okay, so our step one there is our HO and we are HA, and positive auto is at that letter rho greater than 0. HO is the opposite. Step 2, still have an alpha of 0.01. Step 3, look in our statistics and we see we got Durbin-Watson statistic of 1.21. It, gets a little goofy to go much more than 2 decimals because the Durbin-Watson values on our table don't go that far, but I'll do that anyway. Look at our observation, n is equal to 16 in this case. K is equal to 4, right? 4 independent variables, time, quarter 1, quarter 2, and quarter 3. Step 4, let's draw the line. Draw the line. Let's see how big I can make this line and still stay on the page. Okay. Now we're only interested in positive auto, so we're going to have a Durbin-Watson lower, Durbin-Watson upper here. I'll write the numbers up there. And then we have our zones. But here we're just going to call it generically no positive autocorrelation. Okay, we're going to go kick it old school, a little traditional. Not going to care too much about whether there's negative auto or not. We're going to go the old Durbin-Watson way. So let's pull in our table again. Now I just scrolled to where alpha is equal to 0.01, which is what we want. Right? This is our Durbin-Watson statistic. So now I look and see n is equal to 16 and k is equal to 4. And so I have a Durbin-Watson lower of 0.53, Durbin-Watson upper of 1.66. And we don't much care about the other ones. Okay, if you really want to be really technical, there's a 0 up there, and there's a 4 down there. All right, so what does this mean? Where does our Durbin-Watson statistic lie? Well, our Durbin-Watson statistic, which is equal to 1.21214, lies, oh boy, okay, between 0.53 and 0.66. Therefore, we are unable to reject or not reject HO. We're in our I don't know zone. We suspect there's positive auto, but not sure. Really would prefer a bigger sample size in order to be a little bit more definitive. So step 6, we are uncertain whether positive autocorrelation exists or doesn't, or does not exist. Just not sure, right? And that's what the not sure looks like. So that's a little bit of a unique situation with the Durbin-Watson test that's different than all the rest. Okay. All right, let's pull off that table and we'll just chat about the rest of this. So the big thing is when we see that if we have auto is that there's a missing variable and that the effects of that missing variable shows up in error, and shows up in error because there's a pattern in the error. One of the biggest ones is seasonality. We got to get the seasonal dummies in there, and that helps a lot. Okay. Also could be other types of missing variables, but seasonality is a really, really big one. Okay, that it's missing. Now, a couple of little more stat speaky stuff. Even if there's autocorrelation, the estimates for our coefficients are still unbiased. Okay, becomes a little bit trickier if the model is misspecified, so a missing variable. The variances, however, of the estimated coefficients tend to be understated, so sort of the opposite of the problem we had with multicollinearity. So when the variances of the for the coefficients are understated, that means that we tend to have larger t statistics and then by extension smaller p-values. And the consequence of that is we become more likely to say that a given variable is significant when it's not. Okay, so that's a big problem with autocorrelation. There are some corrections to this. Once you get past the, hey, try to figure out what variable is missing and include that in the model, then it gets to be a little bit more complicated, involving some, little more higher level or involved or intricate statistical tools, and quite beyond the scope of our particular experience here. Okay, and so that wraps up our little journey into the Durbin-Watson test statistic.